this next derivative application, something called the Maclaurin Series expansion, may seem to come out of nowhere, but it is actually really important. Now, we're going to use this as a tool. I'm going to leave it to your math teachers to explain why it works. I'm just going to show you between this video and a quick screencastify that it does work. So the basic idea of the Maclaurin series expansion is that any function, or I should really say any rational function, can be represented, well, so any rational function that is differentiable throughout its domain, right? So it is really important that, that you can actually take the derivative of these things. It can be represented by what's called an infinite power series. That's the idea. Now, why would you want to take something and expand it into something that is infinite? Well, the real reason we're going to do this is there are certain functions like transcendentals that are infinite, right? If you think about the transcendental, like sine of x, it just keeps going and going and going and going. So like that's a natural extension there to an infinite power series. Also, we're going to find out that there are certain mathematical operations that are actually really annoying to do to the transcendentals, but are very easy to do to a polynomial. So let's first talk about what a power series is. A power series is of the form, the following. Let's say a power series will look like the following. So we're going to have some sort of constant, which we'll call C0 plus C1 x to the first plus C2 x to the second plus C3 x to the third plus dot 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 plus Cn x to the n, where that's the nth term. This is called the nth term, and it shows the basic form of the term. And that's what a power series looks like, that in each term, successive term, the power gets higher on the x, and the coefficient is slightly different. And what there is for these is that there would be an equation for the coefficient that would be an equation of n. So we'll see how that comes out. So my argument is that any function can be represented as one of these if I know the correct version of what the coefficients look like. Once again, I'm not going to prove to you that that is true. The proof of that is actually not simple at all. I'm just going to show you that it is true and show you how to do something, this Maclaurin series expansion. So I'm going to model this using the sine of x. So here we go. That's what the power series looks like. In the Maclaurin series expansion, the equation for the coefficient is Cn. So the nth coefficient is that you take the nth derivative of the original function, you evaluate it at 0 over the nth factorial, okay? And that is how we do the Maclaurin series expansion. Now I'm going to show you a very specific way in order to do this and the standard of work that's going to be required so that we can do this effectively. Now, why 0? Well, that's the work of Mr. Maclaurin. If this were a different constant, say we're evaluating this at A, some place in the domain, that's something called the Taylor series expansion, and the coefficient has a slightly different version than this, and the power series has a slightly different version of this. What this Maclaurin series expansion is going to allow us to do is what's called center our expansion around 0 and examine the behavior of functions around the specific point, that being the origin. Because when we're dealing with Maclaurin series expansions, we tend to be dealing with fairly small values of x, right? So what is the behavior of this function around the origin? But the Taylor series expansion allows us to do some slightly different expansion work. So that's just a quick aside there. So what does this look like? Well, let's say f of x is equal to sine of x. Well, what does the Maclaurin series expansion want us to do? Well, it wants us to take derivatives, evaluate them at 0, and then get the coefficients. So here's what I'm going to do. I'm going to write the following. I'm going to partition my page into 3 columns. The first column is going to be the function and the derivatives. So here's the thing with the Maclaurin series expansion. When we are doing Maclaurin series expansions, I'm going to hold you to a very minimal standard of work for finding derivatives. Because oftentimes in these Maclaurin series expansions, we're going to have to find 7, 8, 9, 10 derivatives. And if I required you to do the same standard of work throughout, we'd be doing it forever. This one's pretty simple, though, because we know the derivative of sine of x is just simply cosine of x. And then we're going to come down here to the second derivative. The derivative of cosine of x is negative sine of x. The derivative, the third derivative here is negative cosine of x. And as we talked about this ring operation, the fourth, and that's the right symbol there, it's not 4 primes, is equal to then sine of x. And then it repeats. So when we're doing the Maclaurin series expansion, we're going to want to at least have 7 of these terms. Because generally, the way this thing gets phrased is find the first 4 non-zero terms of the Maclaurin series expansion, because sometimes these coefficients come out to be 0. And so I'm actually going to go out to here, 7, so negative cosine of x, and we know then it goes back to the sine, so I'll just do it for completion's sake. So there's the 8th derivative is sine of x. So my first column is all of my derivatives. My second column that I'm going to do is evaluating each of these at 0. Okay? So I found this structure to be really helpful anytime I'm doing a Maclaurin series expansion. Okay? Otherwise, your work is disorganized and all over the place, and it's really hard to evaluate and know that what you're doing. So we know the derivative, or rather, excuse me, when you evaluate sine of x at 0, we get 0. Cosine of 0 is 1, right? 0. This is going to be negative 1, and then the cycle repeats. Super interesting there. So now the last column here is going to be our coefficients. So the 0th coefficient is going to be then f of 0 over 0 factorial, which is going to be 0 over 0 factorial, which is, of course, 0, right? 0 factorial is, of course, 1. It's not undefined, and hopefully you in your math class have had a lot of fun talking about why 0 factorial is equal to 1. Because remember what factorial is talking about? How many ways are there to make it? There is exactly 1 way to make 0. So there it is. C1 is going to take the first derivative over 1 factorial. We know the first derivative is 1 over 1, so then I get 1. C2, once again, I'm going to get 0. You could write that in, but actually all I want you to do, I was just showing you this so that you see what the pattern is. I'm just going to take what I got in the previous column and put it over the factorial. So I got that 0. Next, C3, it's negative 1 over 3 factorial. Now, oftentimes it's actually easier to keep these things in their factorial form, but that's going to be negative 1/6. We'll see why it's better to keep things in their factorial form when you're just trying to present it, but if you're trying to actually do work with it, you're going to want to have the actual values. C4 is going to be 0 over 4 factorial, which is 0. C5, 1 over 5 factorial, 1 over 120. C6 is 0 over 6 factorial, which is 0. C7 is 0 over 7, rather, excuse me, negative 1 over 7 factorial, which is a really big number that I have to remember right now. I'm just going to calculate it real quick. 5,040. And C8 is 0 over 8 factorial, or 0. So there you go. Now we're not done, because what we have to do is actually do the expansion now, because we want to put it into the pattern. So sine of x is apparently equal to C0, which is 0, plus, and then we're going to take C1, which is 1, right, or 1 over 1 factorial, and I'll just write it like that so we can see patterns, times x to the first, plus The next one is just going to go to 0, so I'm not even going to write it. And then plus, I'm going to go 1 or negative 1 over 3 factorial x to the third plus 0 plus 1 over 5 factorial, x to the fifth plus 0 plus 1 over 6 factorial, or 7 factorial, and that's a negative sign, x to the seventh plus dot, dot, dot. So it seems here what I end up with is x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. And now, without even doing this, hopefully you can see what the pattern is, that the next two non-zero terms would be 1 over 9 factorial x to the ninth, and then minus 1 over 11 factorial x to the 11th, plus dot, dot, dot. And that would be the answer to my question. And then the question would usually say, find the first blank non-zero terms, and then you just would do that, and then wherever you got to the right number of non-zero terms, then you just do the dot, dot, dot. So that's how you do the Maclaurin series expansion. Super straightforward and easy in terms of how you do it there. But let's look at what we have here. We have a power series, right? Bum, bum, bum. But if you notice, the only terms that exist in the power series are what? Oh, odd terms. What type of function is sine? Oh, it's an odd function. I wonder if there's a connection between them. And the answer is most definitely there is. Now, the next thing I want you to notice here is that the series goes positive, negative, positive, negative, positive, negative. There's a name for that. This is called an alternating power series. Okay? When the terms alternate every term between positive and negative, there you go. And we're going to see what this is doing to the value, because really what happens here, if you think about what we're doing is we plug in, say I plug in a value here. Now I would have to plug in values in radians here, because that's what that's being evaluated in, and these would be plugins in radians. And so the first term would give you a value, but then I'd subtract off and add on, subtract off and add on and subtract off and add on and subtract off and add on. And so what this is doing is constantly correcting for what that value is until it gets to the right thing. What we're going to find here, and this is going to be clear in the next video, is that we can use, a limited numbers of terms of the Maclaurin series expansion as an approximation for the function. Obviously, we would need the entire infinite series here in order to get the exact value. But if you think about it, if I'm plugging in values like 0.1, these terms start getting vanishingly small compared to the leading terms here. It's only when the x gets fairly large that these terms start to become more significant. But even still, 7 factorial is 5,040. 9 factorial, right, we're talking numbers in the hundreds of thousands. So even if I'm putting this to the 9th, it's divided by hundreds of thousands, and then that's even orders of magnitude smaller. So that's the approximation. Now, the very specific approximation we're going to talk about that we're going to we'll talk about in the screencastify. So I wanted to just very quickly, well, actually, what I'd like you to do here is we're going to try this for cosine of x so we can see that. So f of x equals cosine of x. So either try it yourself, shut the video off, try it yourself, and then turn this back on, and then you can play it at a much advanced rate. But you're just going to watch me here very quickly write out the terms. And we always want to show the same sort of quantity and quality of work here when we're doing this. And once again, right, we're going to hold ourselves to a slightly easier standard of work when we're doing our derivatives, but this is easy because cosine of x is just going to be very similar to what we saw before, because it is in that ring operation of order 4, so I can almost mindlessly write down what I've got here. But only mindlessly because we've already done the work before when we were doing the sine of x. So now in my next column, I'm going to evaluate those things at 0, right? And so this is another one of those moments that you just suck it up and write. You know, the more you sit there and go, oh, I don't want to do it, the longer it takes, right? But if you've got the pattern down, and you should start to see patterns here, because that's the whole point of doing the Maclaurin series expansion, is that we're taking advantage of very specific patterns that happen when you do these sorts of derivatives. So we'll look at some other examples of that in the homework. So now we're going to go C0, and that's going to be 1 over 0 factorial, or 1. C1, that's going to be 0 over 1 factorial, or 0. And now, once you see that a term is going to go to 0, let's just throw down our zeros because we see the pattern. I was kind of holding you to a slightly higher standard of work before showing that plugin before. Here I do want to show the plugin because I think it is actually helpful. Okay. Here we have 1 as well. C4 is 4 over, that's 1 over 2 factorial. There we go. 1 over 4 factorial. And this is a negative sign and a negative sign. See, I'm going too quick even for myself, and I'm messing up. So let me just slow down a bit. Slow is good, and that's a negative 1 there. 120, so that's negative 1 over 7, 20. And C8, actually we've got 4 non-zero terms there. That's going to be sufficient, but I think we see the pattern there. And I'm not even going to put that number there because we don't even care about it. So f of x is equal to cosine of x, which is equal to, let's write down all of our non-zero terms. So the first one is just C0, so it's 1. And then I'm going to get a 0 term. And then it's going to be, a negative term. So negative, I probably should have written the negative there. Actually, let's do plus. I'll do negative 1 over 2 factorial x squared. And then plus 0. And then plus 1 over 4 factorial x to the 4th plus 0 plus negative 1 over 6 factorial x to the 6th plus 0 plus 1 over 8 factorial x to the 8th. Or you can see here, we've got 1 minus negative 1/2 x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 x to the 6th plus 1 over 8 factorial x to the 8th. And you could probably guess what the next two terms are. Negative 1 over 10 factorial x to the 10th, and then positive 1 over 12 factorial x to the 12th plus ... right? There you go. Now, once again, interesting thing here is I have an alternating series. And if you notice here, 2, 4, 6, 8, 10, 12, what's this one actually? Technically, if we go back to here, there is an x, but it's x to the 0, right? To match the coefficient, which is 1. So that is still what we have as even terms. Cosine is an even function. Oh my God, it kind of comes together. So that is the pattern of doing the Maclaurin series expansion. So I'm going to have you for homework by Friday do some of your own, and this is what I'm expecting to see. I'm expecting to see columns of derivatives. Once again, you don't have to show the work there. You should exploit patterns. If you need to do the work, go for it. But otherwise, just write down our results, evaluate it at 0, show me the non-zero coefficients, build the expansion, and then the other video, the Screencastify, is going to go through why are we doing this.